This is a video lecture for Math 283 for Monday, September 7th. And the topic today is three-dimensional coordinate systems. So last week we reviewed Calculus 1 and Calculus 2 material. We're done with that review and we're ready to get into new material. This is section 12.1. Okay, in Calculus 1 and Calculus 2, we dealt with functions of one variable. And so we dealt with function f of x or y of x. And we learned how to take derivatives and integrals of these functions. When we graph such a function, when we graph f of x versus x, we get a curve. Okay. Now, the difference with Math 283 is we're getting into the world of functions of more than one variable. So specifically, when we have functions of two variables, we have to use a new kind of coordinate system. This is a 2D coordinate system, but when we're talking about functions of two variables, we have to use a 3D coordinate system. So we have to introduce a third axis here. And when we create graphs in this 3D coordinate system, we're not going to get a curve anymore, we're going to actually get a surface. So let me introduce this 3D coordinate system as to how do we draw this on the whiteboard. We have three axes. One of these axes is x, one axis is y, and the third axis is z. So this is now three-dimensional space. If you think about it, the real world, the world we live in, is actually it's three-dimensional. When actually it's more dimensions than that. But in the lowest approximation, it's three-dimensional. So this is more like real life than a two-dimensional coordinate system. So we have x, y, and z. These axes are each perpendicular to each other, and we could draw that with little perpendicular signs like this. If we felt like it. Usually we don't include those. The assumption is they're perpendicular. And there's something called the right-hand rule that is used to determine the direction of the z-axis. And so what we do is we place our fingers in the direction of the x-axis. We curl our fingers in the direction of the y-axis. So we curl them like this. And our thumb points in the direction of the z-axis. So that's the convention for the direction of the z-axis. Now, in two-dimensional graphs, we had four quadrants, okay, and those quadrants were dictated by the x and y axes. You had the quadrant where you have positive y, positive x. There's another quadrant for positive y, negative x, and so on. Okay. In a three-dimensional coordinate system, we actually have 8 sections or octants here. And those octants are separated by 3 planes. And so if you think about it, there's an xy plane. Okay, the xy plane, which is this plane right here. There's an xz plane, which is this plane right here. And there's a yz plane, which is this plane here. These 3 planes separate our 3-space system into 8 octants. Okay, so that's an important thing to note. Now, a question arises here. How do we locate a point? X, Y, Z. Or I could call this, let's call this ABC, point ABC. Let's suppose we have a point in 3 space. How do we locate this point on our three-dimensional coordinate system? Well, that's actually really simple. What we do, the x coordinate is always given first, next y, and finally z. So this is telling us what we do is we go down a units down the x-axis, so we come to this point, okay? And then what we do is we go, starting from this point, we go b units in a direction parallel to the y-axis in the xy plane. And so we'll do that. Let's say this is b units here. So that moves us to this point right here. And then finally, the c here tells us the z coordinate. And so for c, what we do is we move up by an amount c units, and this locates the point PABC. So this is a simple way to locate a point in a 3D coordinate system. Okay, that's an introduction to 3D coordinate system. What I want to do now is consider some surfaces we might encounter in 3D coordinate systems. Like I mentioned to you, in 2D, when we create a graph in a 2D coordinate system, we get a curve. When we create a graph in a 3D coordinate system, we get a surface. And so I want to consider some examples here. And we'll start simple. The first example I want to consider is z equals 2. Let's say you're specified that z equals 2 and x and y are not specified at all. What this means is x and y can be anything we feel like. Okay, so the only restriction is that z equals 2. Okay, what kind of surface does this define? Well, let's draw our 3D coordinate system. We can have any x, y, and z is forced to be 2. Well, what this defines is a plane that's perpendicular to the z-axis, that's parallel to the xy plane. Okay. The only difference between this plane and the xy plane is this plane includes all the points that where z equals 2. So this is like the xy, lifting the xy plane up 2 units. And so we can try to draw this plane here like this. And imagine this is z equals 2. So this is a plane that extends out to infinity, that's parallel to the xy plane, perpendicular to the z-axis, passing through the point z equals 2. One challenge, by the way, graphing things in 3D is, I'm drawing these graphs on a 2D surface, a whiteboard, or you'll be doing it on a piece of paper. So the challenge is to try to give a perception of depth. And I'm not an artist, but the more you do, you get better at these. We're trying to draw something 3D on a 2D surface, so that can be challenging. But this is a very simple surface we could encounter, which is a plane. Let's consider some other surfaces. What if you were given the equation y equals x, and that's it? What kind of surface does this define in 3 space? So z can be anything you feel like. Well, let's again draw our coordinate axis system here. This is z, y, then we can draw x here. And in 2D, we know that y equals x is simply a line in the xy plane. And so what I'm going to do is draw that line as a dashed line going out like this. So we know that the points defined by the surface have to lie along this line. Okay. And z can be anything we want. So any point along the z-axis is allowable. And so what this is actually, it's a plane. This is a plane that's defined by the y equals x axis, y equals x line, and the z-axis. So if we draw this plane like this, we can try to do our best to render that plane there. This plane extends to infinity. This is a plane that is perpendicular to the xy plane and passes through the line y equals x and includes the z-axis. So this is another simple surface. If you were given y equals x, that would be your surface. Let's consider a third surface. We'll get a little more complex here. Let's suppose that you were given this equation, x squared plus y squared equals 4. Okay. Now, in 2 dimensions, this is simply a circle. Okay. It's the set of all points that are equidistant from the origin, and here the radius, if this was in 2 dimensions, the radius would be 2. Okay. Well, now we're in 3 dimensions, and since z is not specified, that means z can be any value. And so let's see if we can understand what type of surface this generates. So what I first could do is I could draw a circle that's in the xy plane. But because z can be anything any possible value, this circle can move up or down as long as it moves in a direction parallel to the z-axis. So what this actually defines is a cylinder. I'm going to draw these dashed lines here. What this actually defines is a cylinder. So this is a cylinder centered along the z-axis and having a radius equal to 2. Why is the radius 2? Because this 4 is equal to r squared, so r equals 2. So this defines, this surface here is a cylinder that extends infinitely long up and down along the z-axis. Okay, so these are some simple surfaces we can encounter in 3 space. What I want to do now, the final topic for today, is I want to discuss how we calculate distances between points in 3 space. So let's talk about this. And this will actually lead us to a final type of surface we'll consider today. Let's suppose we have 2 points in 3 space, y. And let's suppose one point is here, and the other point is here. Okay, let's call this point P2, which has the coordinates x2, y2, z2. Let's call this point P1, which has the coordinates x1, y1, z1. And then we'll connect these 2 points with a line. Okay, and we want to know the length of this line. So we want to know the distance between these 2 points. Okay. Well, in 2 dimensions, I hope you guys all remember this. In 2 dimensions, there's a simple formula for the distance between 2 points. And that is given by this. The distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. And I'm not going to derive this formula, but it's very easily derivable using right triangles and the Pythagorean theorem. I'll let you guys think about how to do that. The good news is, in 3 dimensions, the formula for the distance between 2 points is very similar. It's analogous to this. Okay, so in 3 dimensions, the distance between 2 points, the only extra thing is we add a z point, is x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So this is how we calculate the distance between 2 points in 3 space. Now, let's keep that in mind, and I want to consider this final surface today. So keep those distance formulas in mind. Okay, in 2D, if I gave you this equation, x minus a squared plus y minus b squared equals r squared. Okay, this is the equation of a circle with the center at AB. Okay. Now, what is a circle? A circle is the set of all points that are equidistant from some center point. So all these points x, y, this equation defines a set of points x, y that are equidistant from this central point. Let's go into 3 dimensions. Okay. The good news is, so what's analogous to a circle in 2D is a sphere in 3D. So a sphere in 3D is the set of all points that are equidistant from some center point. Okay. Well, if you remember our distance formula between, so let's imagine we're in 3D space. Let's imagine we have some point here, which is the center of our sphere, and then we're considering the set of points that all are equidistant from this center, okay? And we'll call a generic point along the sphere x, y, z. Okay. Now keep in mind, this is not a circle, this is a 3-dimensional spherical shape. So if I could shade it, if I was a better artist, I could shade it and you'd see that, oh, it's a sphere. Okay, well, our distance formula, the distance between the center and this point on the sphere, we know from our distance formula, it equals square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay. So all I'm going to do now is I'm going to square both sides of this equation. And I'm going to replace v with r, because r is the radius of our sphere. And if I square both sides, I get the equation r squared equals, oh, and I'm sorry, the center, I did this wrong. Shoot, I used the wrong letters here. What I wanted to specify was the center is actually, I could call it x1, y1, z1, but I want to call it abc. That's my apologies. So imagine we have a point xy, and we have this point abc. So that by the distance formula, we get x minus a squared, y minus b squared, z minus c squared. If we square both sides, we get r squared equals x minus a squared plus y minus b squared plus z minus c squared. Okay, this is the equation of a sphere in 3 space, which is the set of all points that are equidistant from some center point. And this is our final surface that we'll talk about. We're going to encounter more complex surfaces than these, but it's good to start simple. We dealt with planes, we dealt with a cylinder, and then finally a sphere. So this concludes the video lecture for Monday's class. Let me just explain to you guys, since this is the first video lecture, these video lectures, I try to keep them short and sweet, and I try to give a theoretical summary of the material we're going to cover. I generally don't work any practice problems. The live classes, which we'll have tomorrow, the purpose of the live classes is for you guys to ask me any questions about this material, is for us to work practice problems to get better at doing this material so you guys are prepared to do the homework, and also that time is used to review homework problems for the assignment that's due that day. So I just wanted to explain that. I will see you guys tomorrow at 8 a.m. and we'll talk more about 3D coordinate systems.